Okay.
Hey, all right, good afternoon, everyone. So our last presentation today, we're going to talk about protecting OLTP workloads in a mixed workload environment and what types of resource management options we have to do that. Um, so here's our agenda. I'm going to give a brief overview of different workload types and resource manager features to help out. And then we're going to spend most of our time with Mahalo going over a demo of how to do some of the things that I talk about. So first we'll talk about workload characteristics. And whenever you think about the workloads that you can run in the Oracle database, you can really, for the most part, categorize them into three different areas. There could be OLTP workloads where you have many users with small transactions dealing with lots of rows, and they want to be able to do everything very fast and efficiently. You have data warehouse type queries where you have fewer users compared to OLTP, but those users have really data incentives queries that process many rows. And then there's some type of data loading and processing where you have fewer concurrent users or sessions or jobs which are working on DML over many rows. Now, these workloads could be in separate databases, or you may have a database that has one or more of these workloads running inside it. So when we have workloads running in the system, right, we could potentially contend over different resources depending on the utilization level that we have for those types of workloads. So at the hardware level, there's a number of things we could contend on. We could contend on CPU, we could contend on memory, network IOs, or disk IOs. So let's take a look at each one of these and see what we can do about those. So first is memory. Plain and simple, we just need to avoid competing for memory. You absolutely have to have enough memory available for your workload, your user sessions, right, for your database to run properly. If you don't have enough memory, right, you're going to start swapping the disk and have large performance problems around that. So first thing is we just need to make sure that we have enough memory and allocate it appropriately so we're not competing there. When it comes to network and storage, well, whenever we have any network or storage work, we always do a little bit of CPU along with those. So what we're going to do is focus on CPU, and when you focus on CPU, it naturally limits what's happening on the network and IO sides as well. So that brings us to CPU. So the Oracle database is what we call a process-based architecture. It has a number of processes that work in the background doing things. Plus, whenever you make a connection to the database, right, your connection or session has a process on the database server that's associated with it, which performs the work, all the SQL statements that you send or PL SQL that you send down to the database. And for those processes to work efficiently, they need a few things when it comes to CPU. One is they need to be able to get on CPU as quickly as possible, so not waiting for CPU. And then once they get on CPU, you want them to stay on CPU as long as possible to do the work that you want to be done in your SQL statement. We want to not have it go to sleep voluntarily in terms of the code that we run, and we also don't want to be kicked off the CPU by other competing processes. So when we look at CPU utilization, your CPU utilization really describes the chance of a process getting scheduled. So if we look at CPU utilization at the system level, if my CPU utilization is 50%, that means when I have a process that has a request to do something, it has a 1 in 2 chance of getting scheduled right away. Half the time it'll get on CPU right away, half the time it'll have to wait. And as our CPU utilization increases, that chance of getting scheduled decreases. You can see at 80% CPU utilization, now when I send a request to the database, my process only has a 1 in 5 chance of getting scheduled right away. So that means 4 out of 5 times it's going to have to wait. And that has a noticeable impact on OLTP workloads. With an OLTP workload, you have many users competing for CPU or many sessions competing for CPU. And that session, and you want that session to be able to get on CPU right away to do its work and then get off the CPU so it can have CPU available for other sessions or processes that are waiting. And what we find in the OLTP environment is once you cross that 60 to 70% CPU utilization, right, your response time will start to go up as your processes need to wait to get on CPU, and that has a noticeable impact on performance. So when we look at the different workloads that we just talked about, OLTP, data warehouse type queries, data loading and processing, each of those has specific goals such as OLTP, you want very fast response times. And the way that we design those systems and the different tools and techniques that we use for each one varies a little bit. And when it comes down to CPU, they have little bits of different CPU strategies. With OLTP, you want to save that CPU so that your CPU utilization doesn't go above that 60 to 70% range. But with data warehousing queries and when you're loading lots of data, we have a different strategy is that we actually want to use all of the available CPU, right? So that we can load or process as many rows as possible in a given amount of time. So we end up with these competing roles where OLTP wants to save CPU and the other workloads want to use CPU. So the question is, how can we manage that, right? So a number of different ways you can manage that. And we have different techniques, whether you have multiple databases with each workload running in a different database, or whether they're in a single database. So we'll talk about each one of these briefly. So if you have multiple databases, you could simply put them in different virtual machines on the same server, right? And just allocate CPUs to them, right? So that has the advantage of dividing things up, but may not be very flexible if one workload's not running, right? That CPU is not available for the other workloads. We could do the same thing if we had multiple databases, just using the CPU count parameter to enable instance caging. You can simply set CPU count to a given amount, right? And then that will limit the CPU by that database to the given amount. And you can go in and change that resource manager plan so that you're not always limited, but you do have to have someone or something go in and change those allocations. And then we could also do the same thing in a multi-tenant environment. If we had different PDBs, we could simply set the CPU count at the PDB level. If you're using PDBs, you also have the option of using shares or limits in Resource Manager, and I'll talk about what those mean in just a moment. If you're in a rack environment, one of the simplest ways to manage these different types of workloads and not having to compete for resources is just simply run each workload type on a different node. So OLTP could get its own node, query could get another node, and then they simply won't compete. But if you're running on one server in a single database, right, that's where the challenge becomes a little bit harder. How do you manage those different workloads and not have them compete for each other so that they're affecting the performance, especially of that OLTP workload, which is usually the critical workload. And when we do that, it usually comes down to using the resource manager and the features in there. So the resource manager is part of the database, and it has a number of different features that you can use to limit resources. We're just going to talk about a few of those different features. One is you can set shares, and you can do this at the PDB level, or you can set it at the consumer group level, which is the unit of work that we work on and divide work in Resource Manager. And with shares, you simply divide resources between your different workloads, right, using ratios. And we'll look at an example in here in just a moment. You can also set limits, and when you do limits, when you set limits, right, you're setting hard limits on the CPU that each workload is able to get. Then we also have a feature called parallel statement queuing. And with parallel statement queuing, we limit the number of parallel processes that are available for SQL statements coming in for parallel execution. And by limiting the number of parallel processes, we therefore limit the amount of CPU that they can use. And you can combine all three of these, right, to come up with a more sophisticated strategy to handle the workloads that are running in the system. So what are shares? So shares are simply ratios that you can allocate resources to different workloads. And we're going to look at two different workloads here. OLTP, and queries. And here we've given OLTP 7 shares and queries 3 shares. So 7 parts OLTP, 3 parts queries. And then as they use all the CPU in the system, right, then it will allocate them based on shares. 70% will go to OLTP, 30% will go to queries when we max out the system. So we see here, if OLTP is the only one that's busy, it can use all the CPU on the system. If queries are the only ones that are the only workload that's busy, it can use the majority of the resources. But when they both become available, become active, well, then that's when our shares kick in and we limit OLTP to 70% and queries to 30%. So you can, decide how many CPU resources each one's get, but it only starts to take effect once we max out our CPU utilization. With limits, we can actually cap the amount of CPU by a workload. So here we have not given a limit to OLTP, but we've limited queries to 30%. So if OLTP is busy, it can use lots of resources. But if OLTP is not busy, right, before with shares, query could use all of the CPU resources, but if we set limits here to 30%, it cannot go over 30% CPU utilization. And when they're both busy, well, that's when query can get up to 30%, right? And there's no cap on OLTP. Okay, so next week I have a demo. Mihailo, do you want to talk to
Yep.
this slide and describe it?
Yeah, sure, no problem. Thanks, John. So now we're going to go to a demo where we are going to observe how the system reacts and protects resources, and what happens if the resources are not protected when 3 different workloads are running concurrently. What we will run is an OLTP workload, which we simulate, where we simulate lots of online users playing games. The characteristics here are very short transactions. As you can see, that the response time is millisecond or sub-millisecond. And as such, you can imagine it's sensitive to high CPU utilization. Imagine if the response time, a process that expects a response time for 1 millisecond has to stay in a queue for 1 millisecond, right? That's immediately 100% impact in a way. So this is the workload that we want to protect. This is a sensitive workload. This is what we want to protect. Then we have the queries workload, which simulates users running analytical queries. Each of these queries are taking a few seconds. Each queries will run degree of parallelism 8, and some of the queries will be IO bound. Some of the queries will be CPU bound, by accessing data from buffer cache or memory. And then we will have ETL. With ETL, we will have a single user performing a classical ETL process where it's going to load some data, do some deduplication, do some transformation, and do some aggregation. And all of this will be done with DOP of, here we say 16, but I think we are going to use 24. All right. So can you go to the next slide, John? Right. So just with respect to the OLTP workload, what I want to say here is that we are going to control the workload size by changing think time. And actually, now it's time maybe to go to the demo where I can explain it better by looking at the demo. Let me share. There we go. All right. Okay, this is the demo system. Now I'm going to initialize the demo while that's happening. What I'm going to say here is what you see is panels for the 3 different workloads. So we have the OLTP workload here where we're going to measure the transactions per second, the throughput, and the response time from the database side. The query workload, we're going to measure the query rate per minute, and ETL workload, we're going to measure rows processed per minute or something like that. In the middle section, you have the the performance page that you typically see in Enterprise Manager, where you see all the active sessions, the one they're waiting for. And then we have here statistics that represent how much in percentage, each of the workloads contributes to the CPU utilization on the system. Here we will see some information about how PX servers are being utilized. And then we will see if there is any queuing that will pop up on this particular graph here. Now, what I'm going to do is I'm going to start the OLTP workload. So what this workload is doing is we have 28,000 threads. Well, that simulates 28,000 online users that are performing these transactions. They're making some card moves. And at the moment, each of the threads performs a transaction and then waits 4 seconds. This is think time in milliseconds, 4,000 milliseconds, 4 seconds before it does the next transaction. So it makes a move, waits 4 seconds, then makes the other move. Okay. This represents a low demand on the system. Okay. Let me just resize this graph because this was the initial spike when we started the demo. Just go down to like 10. Maybe that's 6. Okay. So over here with the yellow color, we see the response time from the database. That's DB response time, right? So what we can observe at the moment is that we have about 8,000 to 9,000 transactions per second, and the response time is sub-milliseconds. Okay. We also can observe that in order to perform 9,000 transactions per second, we need about 3% of the CPU from the system. Now, when it comes to the CPU, this system has 48 cores, CPU count is set to 96. With respect to the connection pool sizing, it's static connection pool where we allow 288 connections to the database. Now, we are going to gradually increase the workload, and we are going to do that by manipulating with the think time. So if I reduce the think time for 4,000 milliseconds to 2,000 milliseconds, in turn I will double the workload, because now every player will actually do 2 moves in the same time that it needed to do 1 move with 4,000 milliseconds think time. So let's do that and see what will happen. My expectation is, and better be, that our throughput will double. All right, so the throughput now is about 18,000 transactions per second, which means it doubled. The CPU utilization doubled as well. So from 2.7 or 3% now up to 5.6 or up to 6%. All right, so the database response time actually remained the same. Okay, so we doubled the workload, right? We double the throughput, of course, double the CPU, and the database response time pretty much remained sub-second. Why is that? Well, it's that because we have enough CPU resources available. Okay, even though the users are making more moves, the system has enough CPU capacity to handle the increase of the workload. Now let's double the workload again. One thing that I didn't mention is the peak demand. I said the low demand represents the 4,000, the think time of 4,000 milliseconds. The peak demand in this case will be a think time of 500 milliseconds. Okay, now we are gradually increasing or doubling the throughput, doubling the workload again, and the throughput doubled from about 18,000 to 35,000 transactions per second. Also, we doubled the CPU utilization, which is now 12.7%. And the response time in the database sort of remains in the same ballpark. It's sub-second response time. So far, so good. Now let's go and simulate the peak time demand. So that will be half a second. Okay, so the throughput doubled again. Now we have about 69,000 transactions per second. As you can see, the database response time increased a little bit, and now it's maybe 1.5 milliseconds. that CPU utilization coming from the OLTP workload is about 30%. Okay, so this is our peak demand. Okay, so in order to support the system and sort of allow it to perform 69,000 transactions per second, we will need to make sure that the system has about 30% of CPU available. Okay, one more thing that may happen here is, and I'm going to enable it now, is we are going to measure as well the time spent at the connection pool while waiting to get a connection. So that's queuing time in a way. So you can see now, since we started, since the database response time increased a little bit, that also made us to record some wait time, which is still minor. It's about a millisecond at the application side. Okay, what happens is now, since some of the connections need a little bit more time to perform the transaction so they can release the connection, right? The next thread, the next client process that needs a connection may have to wait a little bit in the queue. However, as you can see, that didn't change our transaction throughput. Our transaction throughput is still unchanged and it's pretty stable. At this point, I'm going to decrease the think time a little bit more now. I'll go from 500 to 400 just to see how much headroom we have for additional workload. So here we are increasing the workload by another 20%. So the transaction throughput increased. Now it's about 85,000 transactions per second, right? The database time increased a little bit, and as a result, we start seeing a bit more of time spent in the queue. But still, the transaction throughput is a bit stable. I mean, it's still stable. Now, in order to support this workload, we need about 43% of CPU over CPU. Now let's go a little bit more. Let's go as far as we can, where we see the throughput gets destabilized, and that will be our kind of red line. Okay, because transactional systems, you want good raw and core performance, core response time to be pretty good, but you also want to have transaction consistency or response time consistency. I haven't started this yet, and this is a blip that happened, which we don't know what. But let's go and increase the think time now to 333 milliseconds. So, throughput increases, CPU utilization also increases. Now it's 50%. And you can see that now by small, as John said earlier, by small increments of the CPU utilization, chances of processes getting scheduled, kind of lowers down. And as a result, the response time may actually be slightly longer because they will have to wait in the queue to get scheduled on the CPU. Now we see, even if we went to 400, but even if we go to 300, we see some variations with respect to the transaction throughput. It's still pretty stable, but let's say that this is our limit, and we don't want to go beyond that. So keep in mind, 500 milliseconds of think time is our peak demand. For that, we needed about 32-33% of CPU, but we can go up to 400 milliseconds or even 333 milliseconds or down to think time. As a result, you will see some time spent in the queuing. And if you go as close we are to 333, we see invariance in the transaction throughput. Not big, but we still see it. Now I'm going to go back to the low demand, and I'm going to introduce the other two workloads. So the query workload, as I said, we're going to start with the low demand. Okay, and the low demand will be one user executing these analytical queries with DOP of 8. I'm going to resize this so it's actually more clear. Again, now these red lines look very big, but that's because we have 6 milliseconds before we had more than that. All right, I didn't start it. Now it's fine. Here we go. So over here we can see one query is running, and again that's DOP of 8. As you can see, because we use DOP of 8, these queries typically use 2 parallel server groups. Each server group uses, as many processes defined by the degree of parallelism. So because we have 2 times 8, we have 16. As you can see here in this panel, 16 processes are currently being used by the query workload. Parallel max servers is set to 384. We also using statement queuing, which kicks in after 256 processes are being used. So at that point, we will start queuing. Right now, let's go and introduce the peak demand of the query workload, and that would be when we have 8 users running the queries concurrently. Again, over here we can see that the query rate of queries executed per minute increases from 17. Now we have 90 or something. And also you can see an increase in the response time, even for the lower demand in the transactional workload. Okay, so we have 8 queries. Each of them may use, or they are using 112 or now 80 something PX servers. They're mostly on CPU, which impacts the ability of the processes coming from for the OLTP workload to get scheduled. Also, what we can observe here is that the query workload contributes with about 30% of utilization, CPU utilization to the system. It actually can vary because this is quite dynamic workload. It may go back and, as you can see now, it's 20%, depending upon which queries are running and so on. Now, what we can do here is, in order to protect our transactional workload, is make the queuing to kick in a bit faster, a bit sooner. So what I can do is I can say, well, I'm going to allow only 16 PX processes to be active at a time while my transactional workload is running, for example. And that will make
Uh-oh.
Oh, we lost me. Hold on.
Yes, and he's running the demo, so it's not easy to take over.
Let's wait a second.
All right.
I just texted him. I think I
Okay.
lost it anyway.
He's probably still talking.
Oh, Mihalo is gone from the network.
Okay.
Can you take
So,
over, John?
Yeah, I'll give it a try here, see if it works.
Okay. Great, thank you.
Oh. Okay, so you guys can see that?
Yes.
Okay, so when we left off, Mihalo was showing that as we put parallel statement queuing in place, well, it was already in place before, but our parallel server's target was so high, right, that it really didn't kick in. But now we set our parallel server's target to 16, which means that we only allow the parallel statements to use in aggregate 16 parallel processes at a time. So you can see when we did that, now the history has gone off here in that pause, but our response time in the OLTP system, right, should have improved a little bit. We can see our query workload has gone down because in effect, we only have one query running at a time. We're telling it to run with 8 users, but our parallel statement queuing is kicking in. So we only have 16 processes that are active and 112 that are waiting to run, right, at the parallel process level. So one query running or one user running queries, seven of them have to wait. So that's one way we could handle that problem. So the next thing that we want to do is to start looking at our our resource manager, and also handle it that way. So before I do that, I'm going to set this back to the way it was, and we should see our parallel statements start to go up again as we allow more processes to run. All right, and there we go. Now we can see we don't have any that are queuing down here, right? They're using more CPU, and we see them go there. And subsequently, we also see our response time in the OLTP go back up. We didn't make any changes to OLTP, but because there's competition for CPU, even though there's not much CPU overall, the competition does have an effect. And you may have noticed that even though we didn't change OLTP, the amount of CPU that OLTP takes goes up a little bit as it has to compete. So now we're going to start introducing Resource Manager with our limits. Okay, so we're going to use the CPU limits that we mentioned before. And here we can see we don't have ETL working yet, but query, we're going to limit queries to using 15% of CPU. So I'll enable that. So we're still going to allow 8 users on the query side to run. Instead of using parallel statement queuing to limit, we're just going to say, okay, that workload on aggregate can use at most 15% of our CPU. And you can see right now it's pretty close to that 15% CPU. When we put that in place, the overall CPU also goes down. So we can see it does have a little positive effect on our response time in the transaction workload as well. Okay, so now we're going to start ramping up again. And we'll change our think time to 2000. So we're going to slowly, just like we did before, start increasing our OLTP throughput by reducing the amount of think time, which is the amount of time that our users spend between playing games, right? So as we cut this in half, it really doubles the demand on the system and should double our throughput. So we see we're going from a transaction throughput of 8,600 here to, after we make the change, right, about 17,000, right? So roughly double. Okay. Now we'll go again, go from 2,000 to 1,000, and we should see the same thing, that we're roughly going to double. All right, so we go from 17,000 here. After we make the change, we can see about 34,000, right? We can see our CPU slowly going up. Every time we make this change by cutting our think time in half, right? Our CPU is going up, but it's not going up at a linear amount for OLTP. There's just slightly more than double every time because we have the effect that competing for CPU itself takes more CPU. Okay, so let's make one more change here. And reduce our think time down to 500. So this, before when Mahalo was doing this, we saw that our transaction throughput went up to about 69,000. So we were at 34,000. And then when we double it, right, we're pretty close there. It says 68,000, may hover around 68, 69,000 there. If we take a look at what's happening, we can still see our queries are running, right? They're limited to 15% of the CPU. And if we look at aggregate, right now we're going into the 50 to 60% utilization range overall. So we're getting close to the area that we normally see, if we go above that, the chance of getting scheduled goes down, and that would affect our OLTP system. So let's take a look at what would happen if we gave queries, right, a little bit more. Say we gave them 50% of the CPU. All right, so as we give our queries 50% CPU, we should see, right, our queries rate going up as they're able to get more CPU, but they're competing with the processes from our transactional workload. And you can see, well, now our transaction throughput starts to go down, our response time starts to go up. If we click on application time, well, we can see a big difference there. Now the actual database time is just a small portion of the total response time. Our database time is about 5 milliseconds, whereas our application time is 130 milliseconds. Looks like we have a spike, right? So we're going back down, but still the application time, right, is a big portion of the response time, right? Because now the database server is so busy that the application tier has to wait for the connections. If we look at what's happening on CPU, well, now we're up close to 80% CPU utilization, right? And when we get that, it's just too much for OLTP. So now let's go ahead and reduce our queries back down to 15%. And when we do that, we should see things start to get better on our OLTP side as our response time goes down and the throughput goes up and becomes more stable, right? And then we can also see the queries start to go down and our overall utilization is now down to around 60%. Let me adjust this graph on the OLTP one here so we can see things a little bit better. Okay, all right. So now we have two workloads running, OLTP and queries. Let's go ahead and introduce our third workload, ETL. Right, in our ETL system, right, that's gonna just have one user logging in or one session which logs in and runs some ETL jobs, right, which load data into the database, looks for duplicate records, performs some transformation, and also does some aggregation, right? We see that start ramping up here, and then we've also limited that user, right, or that session to 10%. So you can see it does have a little bit of an effect on our response time, right? But it's not too bad compared to when we just open the gates and let our queries use 50% of the CPU. So now that we have all three running, you can see we have about 30% idle, a little bit less than that now. So we have about 70% overall CPU utilization, right? And we're just right on the brink of that being too much for OLTP, right? Because we can see our response time looks okay in the database side. It's about 3 milliseconds, but we have this application queuing in orange there, right, going up and down, right? And then from there, we can simply, right, change our CPU limits so we can see, well, what happens if we give more CPU or take away CPU from one of the workloads, right? If we just make a small increase in our query workload from allowing 15% CPU to 20% CPU, let's see what happens there. All right, so we give it 5% more CPU. Looks like we're up to about 78% total CPU on the system right there. And doesn't look like it had too much of effect on our transaction throughput right now. But there we can see it start to spike right in the response time. And when right at that time, same time that we saw the response time go up, we can also see the transaction throughput just dip down a little bit. And my guess is because we're so close, right, to our limits of where we want the system to be CPU-wise for OLTP, we're going to see some instability here on the OLTP side, right? Maybe we want to keep query, right, at 20%, but we want to make our transaction throughput, right, more stable and get the response time back to what it was. Then we could simply take some away from ETL. So we'll lower that from.
Just time check. We have a few more minutes to wrap up. And
okay.
We are done. Thanks.
All right, so this is the last change I'll make in the demo here, and we'll see if that small change from 10% to 5%, right, has an influence, right? So now the change has gone into effect. We can see that our utilization is now around 70%, and it does look like, well, it looked momentarily like it had, right, some benefits there on the transaction side, right? Our response time in the database, right, has stayed about the same, but we can see the orange where we have the response time as part of our, the application waiting, right, has gone down a little bit. Okay, so let me just go back over to the slides to wrap things up. And Mihailo, it looks like you're here. Do you want to wrap things up in this section?
Well, yeah. Well, first of all, sorry everyone. I had an internet problem. Connection totally dropped, so I had to restart my modem. But yeah, I can do it. Or if you want, you can continue. It's up to you.
Yeah, go ahead, Mihailo.
Let me.
Well, I'm sharing. You can just talk to the slides if you'd like.
Okay. So. All right, well, thanks. Thanks, John. So the point here was how to protect the critical OLTP workload. Well, what we did is don't limit the OLTP workload, right? And then we went and determined what's the CPU utilization for our peak demand, right, when the workload was running by itself. And we used the following formula to actually determine how much CPU we have left for the rest of the workload. So what we do here is, I mean, you can get, you know, either we can start on 60 or 70% of CPU utilization. Remember, that's the point, that's the moment when the queues start forming up, and when, you know, the queuing may have measurable impact to the OLTP workload. So you don't want to go higher than that. So you start with that number, then you subtract that CPU that you got before, multiplied by 1.3. And 1.3 is really sort of what we've found a variable that will give us a little bit, you know, overhead for the CPU workload. So that worked pretty nicely in this demo. So whatever is left is what you have for the rest of the workloads. Can you go to next slide? Okay. So if the OLTP peak CPU utilization is 30% by itself, again, the lower limit would be if you use 60, start with 60% utilization and divide 30 times 1.3, so you get 20% of CPU utilization for the other workloads. Or if you want to go a bit higher, be more kind of optimistic, then you would start with 70 and you will get 30% of CPU utilization for the you know, rest of the workloads. Right. So you really need to protect your OLTP workload, right? Because it's really sensitive on you know, CPU starvation, right? You don't want to have the OLTP workload compete for CPU resources, because that may impact you know, transactions and response times and transaction throughput, because this is a transaction throughput, right? Using limits will give you highest degree of control. So that would be kind of the summary of this presentation. And again, sorry about that glitch in my internet connection.
All right, thanks.